This is Medical Physics Part 2, dealing with production of X-rays and X-ray questions. So the first part deals with the production, right? Now in production, he says that the electron bombardment will cause the ejection of X-rays produced by an accelerating potential difference. Now, how does that work? So typically, this diagram actually suggests how much voltage is applied and where do electrons come from. So we already are passing a current through this coil at this point, and the concept actually generates from the idea of thermionic emission. Although not specifically stated here, but thermionic emission is the spontaneous emission of electrons from a high heated metal temperatures, from a high heated surface of a metal, right? So electrons do come out of this high temperature metal, but how do they come to this metal anode? We accelerate them by this potential difference. And how are we doing? How are we trying to do that? You see, this terminal is negative and this is positive. So this actually behaves like a negative terminal, abundance of electron, and this behaves like a positive terminal. So if the electrons are ejected because of thermionic emission, they will be accelerated away from the negative plate and accelerated towards the positive plate. So when these electrons do gain kinetic energy and they encounter the nucleus of the anode, let's say the metal surface, right? These incident electrons decelerate, and when they do decelerate, they release their energy in the form of X-ray photons that are represented over here, right? And this is the name of the radiation that actually, or the process that actually is followed in X-rays. You can research about this online even more than this, but nothing is more required according to the syllabus. Now, when these electrons hit the metal surface, they release X-ray beams, but these X-ray beams are all scattered in all directions. So the first job is to actually make them into a beam form, and that is called making them into a collimated beam. You will see this word in the marking scheme again and again. So collimated beam simply means that X-rays are scattering in all directions. We place a filter in front of them so that we can make sure that all the X-rays coming out of this X-ray tube are actually in a straight line. Why do we need them to be in a straight line? We'll get to that later, because that deals with sharpness and basic image quality, right? So we understand how X-rays work, how they are actually producing X-rays, and where this accelerating potential difference is going to help. We'll get to that later as well, because that deals with contrast and imaging quality, right? So we have covered point number one. Point number two is imaging the internal body structures, how we do that, and what is the meaning of contrast. So the second part of this video will deal with the image production, right? Let's move towards that. So the energy of the X-ray photon depends on this equation. How does this equation work? We know that from quantum physics, the energy of a photon is actually E equals to hf, where h is Planck's constant and f is the frequency of the emitted photon. And up to this point, where does this come from? So we know that from A2, from electrostatics, we understand that if there are positive and negative plates or charged plates, and we know the voltage, right? And if there is an electron being placed between them, positive charge for that matter as well, no matter wherever it goes, it will gain some energy. And that is how we know that voltage is equal to work done by charge. Now, let's take Q over there, and this becomes QV equals to work done, which is represented in joules. Energy is also represented in joules. So whatever energy we are providing to this electron, due to the acceleration voltage, due to this potential difference that I just explained over here, whatever voltage we provided, this voltage is converting into energy, into kinetic energy, right? And that kinetic energy then eventually converts into the photon energy of the X-ray when it hits the metal target, right? So we understand how this process works. That's why we've equated the energy of acceleration, the work done in acceleration, to the energy of the emitted photon. This is how this equation actually comes into place. Now, he says that we can control the frequency or the wavelength of the emitted X-ray photon by changing the potential difference. And that's pretty much it. Why? Because E is the elementary charge, which is 1 into 10 raised to the minus 19. So we can't change that primarily because that's a constant. H is a Planck constant, which is 6.63 into 10 raised to the minus 34 joule seconds. So what we are left with is just this voltage. So if I increase the voltage, the frequency increases, and we understand that if we increase the frequency, the energy of the photon increases. So you will see this in the book in another way, because we know that V is equal to F lambda, If you make f the subject of the formula, take lambda over there, this becomes v divided by lambda is equal to f. And since v, the speed of light, is constant for all the spectrum, we get to this equation, which is f being inversely proportional to lambda. Another way you will see this statement in the book is that increasing the voltage decreases the wavelength. So yes, if increasing voltage increases the frequency increases, so mathematically speaking, lambda will decrease, right? So one way to talk about this, you will find this in the book in this way. Okay, then we move towards the imaging process. So how does imaging of an X-ray actually work? We are actually trying to take advantage of this idea that X-rays attenuate, or you can say lose energy through bone much faster than they do through flesh. So when they pass through flesh, the loss of energy is less. When they pass through bone, the loss of energy is much higher. So that is why you see a contrast on the X-ray image film, because bone has absorbed almost all of the X-ray and flesh does not. Or you can say it does, but not to the extent that the bone has absorbed the X-ray, right? So that is the idea of contrast. That is the idea of imaging of the X-ray. But let's move towards different qualities and aspects of the X-ray. This is another image of the same idea. You see, X-rays can pass through flesh or soft tissue by losing least amount of energy. And when they pass through anything that has a bone, yes, this section, this is flesh, this section is also flesh, but this section is bone. So this loses a lot of energy while moving through bone, and when it comes out, there is a large difference between the radiation or the X-ray coming from the flesh and the X-ray coming from the bone, right? And we take advantage of this idea to create the contrast. Now, the first thing while we are taking the X-rays is to reduce the dosage or the overall exposure to the person, because we don't want an overexposure, because overexposure will eventually cause cancer. So what we're trying to do is we're trying to reduce the exposure times, reducing the dosage times. And how do we do that? We use image intensifiers or phosphorus image intensifiers. What they're trying to do is whatever X-rays are received after they cross the person, they're passed through this phosphorus layer, which actually receives these X-ray photons and releases more photons that are in the visible spectrum. So we receive less photons, less energetic X-ray photons, and we increase their intensity by using this phosphorus, right? And this phosphorus emits even greater or more number of photons, eventually leading to a higher output, or you can say a better output or a clearer image on the X-ray film. Again, the purpose of this was to reduce the exposure. So we're introducing less energy photons, or you can say we're trying to reduce the exposure time, but we're amplifying it by using a phosphorus layer. You just have to memorize that phosphorus image intensifiers are used to reduce the exposure times to prevent any overexposure, which may lead to cancer, right? Then we have contrast. What is contrast? Now, contrast is basically the degree of blackening or the degree of black regions compared to the degree of white regions, right? Now, we can see that this is, we don't need to understand that what is this underexposure, if this is the optimal and this is overexposure. This is just here for your idea, what we're talking about in terms of contrast, right? So we want something that is optimal. We don't want underexposed, we don't want overexposed, because overexposure will be harmful. Underexposure will not be good enough for a medical technician to understand what's going on, right? So how do we do that? There are two terms, softness and the hardness of X-ray. Now, soft X-rays are referred to those X-rays which have low energy and they have low frequency. Again, E equals to HF, and if frequency is low, then lambda will be larger. We have developed this idea. We understand that this is what the relationship between F and lambda is, so that's why we say it in this way as well. And if the energy is low, then large exposure, you can say the exposure has to be taken for a longer time so that an image can be produced, and this is not desirable for a patient. We want the exposure times to be as minimum as possible, and we want during that exposure time, we want the image to be formed successfully. So we use hard X-rays for this process. And what are hard X-rays? What are the qualities of hard X-rays? They have high energy, and of course they will have high frequency, and they will have a smaller lambda, so that a short and quick burst or exposure of X-ray will be good enough to produce an image on the X-ray film, which will be safe and will cause minimum exposure to the patient, right? And how do we do that? We increase the accelerating potential difference between, and then of course add a filter to absorb the soft X-rays. Now we go back to the potential difference equation, which we did over here, right? we want to increase the hardness, we want to increase the energy, so simply increase the potential difference of the accelerating potential, which will increase the frequency, and we will have hard X-rays at our disposal to be used for the patient, right? Another way to increase the contrast is to use barium meal, which is again going to act as an intensifier. Barium absorbs X-ray photons much greater. It absorbs radiation much in a much concentrated way. So what they do is to reduce exposure times even more. They give a barium meal or an injection to the patient, which increases the absorption of X-ray in that particular target area, wherever we are expecting that a tumor or cancer is forming, right? Okay. Then we have these questions. What you can do is try to solve these questions I've mentioned in the slide in this lesson. Memorize their answers because they generally cover the whole topic of X-ray and CT scan. Okay. All right. So he says, what is meant by contrast? Again, as I explained earlier, it is a difference in degree of blackening between structures, right? Then he says, by reference to your answer in A, state X-ray of the model has good contrast. You see, this is part B of this question. In part A, there was a numerical question in which one part had this answer, the other part has this answer. How will you differentiate? How will you you can say this with certainty that the image has a good contrast? You simply divide both answers. If the intensity that you received, let's say, from the soft tissue will have a higher answer, and the one that you received from the bone will have a smaller answer. So you divide this answer with this one, or the other way around, and you will see that the answer should be greater than 1 time. If the answer is greater than 1 times, it is twice, thrice, or 4 times. This is actually 15 times greater. But you can say there is a difference of 15 times between them. So that means it has a good contrast. So you'll have to say this in this answer, that there is a large difference between them. And you probably may not be able to just take the difference of them directly. That's why you take the division to find the ratio between them, because this makes it much more clear that there is a difference of 15 times, which is of course going to be good enough for a good contrast. Then we have this question. Okay, it deals with the hardness of the X-ray beam. He says what is meant by hardness, and of course it deals with the penetration of the beam. It is controlled by the accelerating potential that we understand, right? Greater penetration, shorter wavelength, higher frequency, higher photon energy. And of course, it is controlled by the accelerating potential, which is asked in the second part. How can it be increased or decreased? By changing the accelerating potential, which again comes from the same equation, that HF is equal to QV. We are dealing with F equals to QV divided by H. So this is the potential voltage that we're increasing to control the hardness of the X-ray. Okay. Moving on towards the sharpness. This is a slightly tricky topic because this actually stems from O-levels light and lenses topic, but let's go through that. He says, suggest 2 causes of lack of sharpness of the X-ray. You see, the scattering of X-ray, lack of collimated beam. This is what I've explained in the earlier part of this lesson. The anode area is large, the beam has low potential difference, of course, causing soft X-ray. But what's with this scattering of X-ray and anode area being large and aperture large? What is the meaning of this? You see, if this is the structure of the person that you're trying to figure out, if this is the patient, and if this is how X-rays are coming towards you, if the X-rays are not in the form of a beam and they are scattering like this, if the X-rays are scattering like this from all directions, then on the screen there is going to be a shadow produced and not a clear image will be produced. Why? Because they're scattering. This effect, you can say, comes from this idea, partial shadow, penumbra. You can search this from O-levels and IGC syllabus as well. So what that does is that this part of the image is formed at this place. Okay, good enough. But wherever these radiations are also coming, there is also partial shadow over here as well. So which disturbs the sharpness of the image. We want the image to be as clear as possible. So in order to do that, instead of scattering X-ray beams, instead of these waves, what if we had the waves like this? If the structure of the radiation of X-rays was like this, very straightforward, very straight up like this. If this is how X-rays were coming towards the person, right, then we can see very clearly that the edges of the object formed on the screen would be very, very clear. Instead, what we get in this situation or in this scenario is something like this, where the X-rays are scattering like this. So it will reduce the sharpness. Okay. So how to improve that? How do we control that? How can we make it better? That is going to be found in this question and the answer of this question. So I've included this because you can memorize the definitions of sharpness and contrast from this part, and you can clear out how to increase the sharpness from this point, or what factors affect the sharpness. So you can memorize these answers. I've already explained them in this diagram, what sharpness looks like and why sharpness is actually needed. Okay. Photons scatter, of course, right? And there is no collimator, there is no use of lead grid. You can see that this lead grid was also mentioned over here as well. So it's all based on memorization. We know the common questions, we memorize those answers, and expect that examiner is going to ask you the same questions. The next time around, he is going to ask you the question about X-rays. Okay. All right. Then we move on towards characteristics X-ray. This topic, although not mentioned in your syllabus, but I've seen questions like this. You can see that this was asked in this way, in this paper. You can memorize the marking scheme of this question. It's a good question in terms of extra knowledge and extra points. What is characteristic X-ray? Basically, the type of anode that we use. For example, I go back to the X-ray machine. Okay, so this anode, the type of anode that we're using, probably, let's say we're dealing with tungsten, we are dealing with, let's say, magnesium, we're dealing with copper, we're dealing with any other material, although one of them is used for X-ray, not all of them. Now, the type of metal that we use will also show some results on the screen like this. You see, by this time we understand from quantum physics that every nucleus has shells, and every nucleus, shell number 1, shell number 2, and shell number 3 will have different forms of energy, will have different levels of energy. That's how we identify what atom we are talking about. Okay, so let's say if this is copper and let's say this is tungsten, even if we are dealing with their first shell and the second shell, they will have different energy levels between them. That's their own identity in terms of quantum physics. Okay. Now, when that happens, sometimes when we are introducing these electrons, they interact with the valence shell electrons like this. And somehow they will be responsible for ejecting these electrons over here or in other random directions. So what happens is that an electron from the outer shell is going to take its place because it is knocked out. And in doing so, as it comes down, it will have to do this by releasing energy. And in what format is it going to release energy? It will be releasing energy in the form of an X-ray photon. Right now, these X-ray photons are called characteristic X-ray photons because they will have specific energy levels and they will only be unique to that atom that you are using. They will only be unique to that metal that you're using, because tungsten will have a different energy level and the energy released by that element will be showing up at somewhere else. Right. So characteristic X-ray only tells you what type of metal anode they were using. Okay. All right. Then we move towards the attenuation equation. So we are done with the second part. We are going to move towards the third part, and then we'll move towards CT scan, which is part number 4. So the attenuation equation, again, it is going to be carried from the ultrasound, right? The equation exactly follows the same path. That is I naught e raised to power minus mu x. What is mu? What is I naught? So I naught is the original intensity or the original radiation that is being received. Mu is absorption coefficient, exactly like X-rays, exactly like ultrasound, absorption coefficient. And X will be the thickness. Make sure that the units, let's say if this is in centimeters, this should also be in centimeters, although that is primarily, the absorption coefficient is centimeter minus 1. If this is in meters, then this should also be in meters. And if you're dealing with millimeters, then of course, it has to be in millimeters. So if this was millimeter, minus 1, then this would also be millimeters. You have to make sure the units are same. You can't change the unit of absorption coefficient, but you can change the prefix of the thickness. Be careful about that. Let's see how to use this equation. So first we have this system. Again, the diagram exactly the same that we've dealt previously. Okay, this one, this diagram, right? So now he wants you to calculate these things. So it says what's going to be the difference or the ratio of intensity transmitted through bone and intensity transmitted through muscle. So we're just going to use the attenuation equations to simply write down all values over here. So let's write down for the bone. So for the bone, this is going to go like this. I naught e raised to power minus mu x, of course. Mu is this one, which is 2.9. So 2.9 into The thickness is 1.5. So this will be 1.5 divided by the intensity through muscle. Now the muscle's value is also given in the table. Okay, I've chosen this common example to fully understand how the equation is actually going to work. So e raised to power minus mu is 0.95. Now you can see that the absorption of the bone is much higher than the absorption of the muscle. That is what sets up the contrast. Okay, and then the thickness is 4 centimeters. So through the muscle, it has to travel 4 centimeters. Now, I naught is going to get cancelled out, right? I naught gets cancelled out. Why? Because you've introduced, let's say if this is your muscle, this is your bone, this is muscle, you're introducing the same intensity of I naught to the muscle. And when you're trying to calculate the equation, then that becomes I naught e raised to power minus mu. So both of them receive the same radiation. That's why both are going to get the I naught factor. Whatever they received was same for both of them. Okay, that's why it's going to get cancelled out mathematically. So you're left with just this bit of mathematics. When you calculate this, your answer is going to be 0.5769. You can pause the video and try this on your own, which will be written down as 0.58 up to 2 significant figures according to the CI syllabus. Now we move towards a CT scan, which is simply a 3D X-ray. What they do is take the X-ray from different angles. So they keep rotating this. They introduce radiation from this angle, then they introduce radiation from this angle, then they introduce it from this angle, which helps them to create a three-dimensional image of the structure of the body, right? And of course, there is running a risk. We are running a risk of this at this point, which is that first, just a single X-ray would be causing some sort of exposure or some value of exposure to the patient. Now we are introducing X-ray from different angles, which is of course going to be done many times over. The exposure of the patient increases, but modern technology we have tried to take care of this. The exposure now these days of a CT scan is less than one X-ray conducted in the previous days when X-ray was actually invented. Okay, so they say that it's safe, but of course some radiation is still absorbed by the body. But anyways, we just need to understand that this is actually being done from many angles. So these are fixed points, fixed answers for an X-ray question, for a CT scan question, a 3D image from different angles, slices of 2D images combined by a computer to make a 3D image. Images can be rotated and viewed from many angles, stored in a computer or a powerful computer, right? You can follow up this question in this part and just memorize the answer of part A for a CT scan. I think this is a 4 or 5 mark part. He's going to ask these questions one way or the other, right? So just memorize these answers. But we understand how this works, right? So we just need to memorize the marking scheme so that if he asks us the question, we don't need to find this in the book. We can just copy the marking scheme. Now, one question in terms of a CT scan mathematical question comes like this. He's going to ask you what are the cell values of the patient if this is what is stored in the computer. You see, if this is your patient, which is placed over here, when you introduce the radiation from this angle, then you introduce radiation from different angles like this one, and like this one. The computer stores the data of the patient over here and then compares it and then performs some calculation on it to fully understand what the actual values of the patient are going to be. We're not going to get into the detail how those calculations work. We're just going to learn the method how to solve it. Okay. So how many angles has the patient been identified to or been exposed to? You see, first the radiation was introduced from this angle, then from this angle, then from this angle, and then from this angle. Ultimately, of course, leading to certain values stored in the computer, and then the computer performs calculations. What are those calculations? First, you count how many angles you exposed the patient to. So the number of angles will be counted like this. First angle, angle number 2, angle number 3. So the number of times the patient was rotated is 3. Now memorize and keep this number on the side because you will use this in a mathematical calculation. Okay. Now, then he tells you that the background radiation is 34. This is going to be part of the stored answer because the X-rays and the computer are also being exposed to background radiation, and there is no way to look beyond this. There's no way to stop this. So first, what we're going to do is we're going to subtract these background radiations from every cell, although these cells are called voxels, right? Just a term in the book as well. So 49 minus 34 then 61 minus 34. Every cell will be subtracted from this value. So 73, let me write this down somewhere else. So 73 minus 34, then we have 55 minus 34. Then after you've taken the subtraction, please remember this is going to be done after the subtraction. You will divide this with the number of angles exposed, or the number of angles used, or the number of angles which were given to the patient in terms of X-ray. So then you divide this with 3. Divide each cell with 3. Please make sure that you don't divide this number with 3 and then take the subtraction of 34. That will give you the wrong answer. We are first going to subtract the background radiation, and then we're going to divide the answer with 3. So as a result, you will get these answers to be P will come out as 5, Q will come out as 9, and S will come out as 13. R is going to come out as 7. Then you can fill these answers in this place. Okay.